equation has this additional term, and the energy is given here, 1/2 kx squared, and it has this additional term of exponential decay, right? Euler's number, e to the minus b, I think it's t squared over s. But anyway, okay, so, well, we're not. You've seen it. And we're not really going to test on it. But. Okay. So I don't know if I gave you a problem. I may have given you a problem that deals with it. If I did, you can just skip that. Or you can learn it if you want. Now, just a little bit on forced oscillations and resonance. So you dampen oscillations where? In your shock absorbers. There you go, Mr. Carlos, you're the car guy. Right? You dampen an oscillation with your shock absorber. Say you have a fluid, and they, so it doesn't keep oscillating up and down. It just kind of oscillates, stabilizes. Suspension is a very important safety feature. Cars, and they've got way sophisticated, computerized, creates stability and improves the safety. Because when a car rocks, right, what it's doing is shifting the center of mass of the car, right? So you go around the turn, or you have to make a quick lane change, and the car dips to one side, and then the car back and forth. The old cars were more like that than new cars. Even the less expensive cars are quite stable in relation to the old cars, so they're much safer, quicker, and people change lanes more quickly and more accident avoidance. But of course, also empowers them to drive like maniacs, weaving in and out of traffic. So, but anyway, a little bit on damping, but you can dampen lots of oscillations, right? Okay, well anyway, forced oscillation is sort of the opposite. Instead of dampening, you might want to increase the oscillation for different reasons. And so that is, sometimes you have what's known as a forced oscillation, and that's where you add energy to an oscillation. So for example here, I have my little mass here, and it's oscillating, right? And a forced oscillation is where you add some energy, right? So I can add energy to that oscillation. See? Now, notice, so I'm driving the oscillation, right? But you notice that my force is not matched to the natural oscillation. So we have a natural oscillation, right, that derives from the mass and the spring constant. And I can drive it with a frequency that doesn't match it, but if I drive it with a frequency that matches it, then I get what's referred to as a resonant condition, where I'm adding the energy in such a way that is in sync with the spring, and that drives to a larger amplitude. So just try this for a second. So we're oscillating here, and now you can see it starts amplitude. Here's my natural, and then I start to. I can't even do it. I need more weight, more. But as I start to drive it, in sync, then the oscillation quickly goes high because I'm adding the energy. That's called a resonant condition. And so In some cases, you want a resonant condition. In others, you don't. So if you have a building, everything has a natural oscillation, and you try to figure out what is the natural oscillation of the building from an earthquake, from winds. Not that familiar with it, but you can kind of use your imagination some. And that natural oscillation, you want to, prevailing winds, you know, you want to design the building to resist that, or maybe you put in a system that resists it, like this dampener we're talking about, so that the winds don't cause the building to get into, you know, a forced oscillation with the wind, which would cause it to amplify the oscillation. See? But that's any type of structure. From energy, from some energy input, usually mechanical. Now, on the other hand, in electrical circuits, in the LC circuit, you have an inductor and a capacitor, and you have the frequency of current oscillating. You want to match the frequency of the circuit with the circuit frequency, right? Where the electricity is moving back and forth in a regular pattern. And use these in radios where the wavelength that comes in that you want to receive, right? That frequency, you tune your radio, which means what you do is you change the electronic oscillation so that it matches the frequency coming through the air, okay? And when you match it, it creates a forced oscillation, and that amplifies the signal. So that's how you tune the radio. When you get to that signal, it amplifies the signal, and then you can amplify it some more and listen to, you know, the Cincinnati Reds in Ohio or something. You can listen to the weeks. You can listen to whatever you're listening to on the radio. So the old radios were a dial. Nowadays they're digital, but they're still the same idea. Instead of a dial, you have a digital tuner. It's the same basic idea. Okay, well anyway, just a little bit on forced oscillation. And we won't test that, we'll talk about it a little bit. Now, so they're showing you there, let me just point out, they're just showing you there that resonance condition occurs, you know, at a particular frequency, using the natural frequency, and greatly increases the amplitude right at that point. Sometimes we do that lab if we have some time, but summer we just don't seem to have as much time. But anyway, okay. Here, the building falls over. It's in a forced condition from the shaking of the ground. Now, I want to do a little bit on waves, see what we can do. Just a little bit. So, whatever we get done, we'll cover. Now, on Tuesday we will we'll do problems. Okay. Make sure that you feel prepared. Since we did the fluids in the handout, we will only have 15 and whatever we cover in 16. So we'll make that clear. Okay. And the number of problems, I'm not sure how many. Anybody count the problems? Maybe somewhere around 80 or 90. It's not going to be the 130. But anyway, something like that. But Monday we will. Tuesday we will settle all that. We'll make sure that it's clear. We'll know where we are. Okay, so we're talking about types of waves, and your author breaks it down into 3 waves. We have mechanical waves, and that's the one that we see all the time. There's a water wave and a sound wave, and seismic waves when the earth vibrates, and waves on a string or waves on a cable, like the cables that hold the bridges, you know, they oscillate. Or an electromagnetic wave, and this is a wave of energy, of electricity and magnetism, and you will look at that in second half of the course. In matter waves. Matter waves are a new wave discovered in the 20s, and this is the idea of a particle as a wave, where the energy is spread out, and even though it's been around for almost 100 years, it's probably not that familiar to many people. I don't know. But anyway, so those are 3 types of waves. Now, so for those waves, we have really 2 types of waves. We have a transverse wave and a longitudinal wave. And in a transverse, the particles oscillate in the same direction as the wave motion. No, not the same direction. Did that wrong. Particles oscillate perpendicular to the direction of the wave motion. We'll go over this in a second. And in longitudinal, particles oscillate parallel. Same thing. Particles oscillate parallel to the direction of the wave motion. Okay, so let's look at that. So here's the classical wave, like the water wave, right? Or the wave on a string. And when you have a wave, it travels, doesn't it? So think of the ocean waves. You go to the ocean, and what do you see? You look out there in the distance, and you see the wave coming in, don't you? You ever do that? You go to the ocean, and you look out there. Ocean shorelines are infinitely fascinating for many reasons, but anyway, out there, you see the wave, and then you watch the wave come all the way in. It travels, doesn't it? The waves travel. And you see the flag waving in the breeze, you know? It waves in the breeze. It's waves because, you know, the wave starts on the inside